Alright, hello. So we are going to start our discussion of the last chapter that we're going to cover this year, chapter 16, talking about light. And so the section that we're going to cover today is Illumination, section 16.1. Okay, so when we talk about light, we talk about this ray model of light. So we know that light travels in a straight line, and Newton believed that light was a stream of fast-moving, super tiny particles that he called corpuscles, which kind of sounds like an infection or something. But we also know that light behaves as a wave. If you remember back from chemistry, we talked about how light behaves as a line and a wave, and that has to do with the electrons jumping through orbitals and giving off energy. Well, for our purposes, we're going to look at the ray model of light, which says that light is represented by a ray that travels in a straight path, and the direction can only be changed if there's some sort of obstruction. So kind of like sound, it hits the obstruction, reflects back, and is changed. So ray optics, or geometric optics, is the study of how light interacts with different types of matter, and that's what we're going to look at in this section, how different things are illuminated. Okay, so before we can do that, we need to talk about sources of light. So a luminous source is the object that emits light. It's luminous. The illuminated source is the one that becomes visible as a result of light reflecting off of it. So most objects that we see are illuminated. The luminous source would be like a light bulb or something, or the sun, something that is emitting light. Well, there are also lots of types of media that light can transfer through or reflect off of. Things that are opaque don't transmit light at all. So like a brick wall, very good example of something that won't transmit light. Something that's transparent will completely transmit light. So air, glass, anything that's pretty much completely clear, you look through it and it's not distorting your view. Translucent objects transmit light, but you can't see the objects clearly. So like a lampshade, frosted glass, things like that are going to be what's called translucent. Light still transmits, but it's distorting the object. Translucent and transparent media can also reflect light. Opaque can't, because it won't transmit light at all. Okay, so now we've talked about mediums and the object that emits light and that gets illuminated because of light. So now let's talk about quantity of light and how to measure this. Well, there's a couple variables we need to talk about. The first is luminous flux, which we're going to use a capital P for. And this is the rate at which light energy is emitted from a luminous source. This is measured in what's called lumens, or LM. And so, for example, a 100-watt bulb emits 1,750 lumens. So it's the rate at which light energy is emitted from that bulb. The other part that we need to look at is illuminance, or capital E, and this is the rate at which light strikes a surface, or the illumination of the surface. So luminous flux comes from the light source. Illuminance is the rate at which light illuminates whatever the surface is the light is transferring to. This is measured in lux, or LX, and it's lumens per square meter, because it's how much of this area is being illuminated. So LM per meter squared, or LM per any area, whatever you're measuring your area in, but meters is the standard unit. So let's look at an example. So let's say we want to know the illuminance of a sphere's inside surface. Let's say you have one of those, are they like the Japanese paper lanterns? That seems to me like maybe that would be a good example. So the luminous flux is 1,750 lumens. We have a 100-watt light bulb hanging from the center. And the surface area of the sphere is 4 pi r squared, because that's the surface area of the sphere. And we know that the radius, or the distance from the light source to the outside of the sphere, is 1 meter. And so we know the surface area then, excuse me, is just 4 pi. So if we want to calculate the lux, or the illuminance, this is the luminous flux over 4 pi, because we know how much light is being emitted and we need to look at the surface of the sphere. And so that gives us 139 lux. Okay, well, let's look at the relationship between these two variables. So what if the sphere, instead of being 1 meter in radius, was 2 meters in radius? Well, the luminous flux would still be the 1,750 because we haven't changed out the light bulb, so that's staying the same. But now it has a larger area that it needs to illuminate. Now it's 4 times larger because the radius is squared, and this becomes 16 pi. So the illuminance is going to be 1/4 the 1 meter radius. Because we have this much larger area to illuminate, it's going to get illuminated less overall, because our light's not getting any different. So for this one, it would be 34.8 lumens. let's say we had a 3-meter radius. So this would be 1/3 squared, or 1/9 of the radius. And so it's an inverse square relationship because of the radius being squared. Illuminance produced by a point source is proportional to 1/r squared. Point source we would consider to be a light bulb or something where it's coming from one area, or one point. Okay, so we can also talk about luminous intensity. So a candela, or CD, is a measure of luminous intensity. And to calculate that, it's luminous flux divided by 4 pi. So luminous intensity of a point source is the luminous flux that falls on an area of 1 meter squared of the inside of a 1 meter radius sphere. So it's just like a standard or a measurement. Okay, so let's talk about how to illuminate a surface. We talked about the difference between the 1 meter sphere and the 2 meter sphere, and how the 2 meter sphere wasn't going to get illuminated as much due to that inverse square relationship. So to illuminate a surface better, you need a brighter bulb, you need more luminous flux, or you need to decrease your radius, move your light closer. If you assume that the light source is the point source, so like the light bulb is coming from that one specific point, and light from the source strikes perpendicular to the surface of whatever it is you're measuring. So we would assume that if we had a desk, the light would be up here, and the light is pointing directly down. Now we know it kind of goes out in all directions, but for our measurement purposes, that's the distance that we're going to measure. I guess I could draw a picture. So if we have a desk, here's my light source, we're assuming this is our measurement. So point source illuminance, so to calculate E, is equal to luminous flux divided by 4 pi r squared. This does not work for fluorescent light bulbs, mainly just light bulbs and other point sources of light. Okay, well, we're talking about light. Let's talk about the speed of light. Initially, light was thought that it traveled instantaneously because it does travel quite fast and we were unable to measure it. But today we know that the speed is 3 × 10⁸ meters per second. And this is kind of a standard like the acceleration due to gravity. So it's either something you're going to want to put on your note card or just know. Several people have experimented with the speed of light, specifically Galileo, Romer, and Michelson. And Michelson won the Nobel Prize for his experiments with light because he did speed of light in a vacuum. And this is the variable c. So if you think about Einstein's E = mc squared, c represents the speed of light in a vacuum, which we're going to use as 3 × 10⁸ meters per second. In 1 light year, light travels 9.46 × 10⁻12 kilometers, which is a whole lot. So light travels pretty fast. Okay, we are going to go over these examples in class, and here is the homework for you to practice on. Have a good day.